In this tutorial, we will solve a 2D Laplace equation of temperature field. So in your tutorial, there's a problem, and this is actually a problem from your book, and you can look at page 856 to see it. So this is a block of, could be a room or some material, and the temperature at the four sides is given, and we are asked to find the temperature within at these 9 grid points using the knowledge that the temperature field obeys the Laplace equation, which is the Laplacian of the temperature is equal to 0. And as we covered in the class, this is the second derivative along x plus second derivative along y is equal to 0. And we can approximate that using the finite difference approximations and set it equal to 0. And if we let the spatial interval along x and y direction to be equal, then these can be cancelled and we get a simple linear equation where the value, 4 times the value at a given node minus the neighboring values along the x and along the y directions is equal to 0. And so we can create this equation for at each of these nodes, giving 9 equations, and there are 9 unknowns which can be solved simultaneously to find the answer. So in this case, if we write those 9 equations, and I have done this just to show you how to do this kind of development of this matrix, but later on we will also look at an iterative method which prevents us from creating these matrices. But if we look at the matrix itself, it turns out to be a diagonal matrix, but it's not just a simple diagonal matrix, it's a block diagonal matrix. So these 3 by 3 elements, they form a small block, -4, -4, -4 along the diagonal, and 1, 1 along the off diagonal, and then 0, 0 along the corners. And then this piece right here, this little block, is repeated along the diagonal. You can see that this piece is not 1. This element over here and over here is not 1, which means it's not, as a whole, it's not a tridiagonal matrix, but it has it's called a block diagonal. So a block of matrix is repeated along the diagonal. But then if we go away from that, we also have another diagonal of 1s coming at the 4th point or 4th element in the first row. It's kind of starts shifting, so forms a diagonal, and at the same time along the 4th row. So 4th column and 4th row are repeated. So Matlab provides us some functions that can be used to do this. But then once we set up these two matrices and solve for P, then P is T11, T21, all of these values. And so if we want to plug those back in, we have to put those back here in this matrix, and that part itself needs care. So let's go to Matlab, and let's first define a blank 5 by 5 matrix. So this is temperature. So I've defined it as not a number, and it's a blank field. And from our temperature field, we know that this is our first row. So this is before first row, we have 0 degrees Celsius. So and that's why we have a 5th row here. So that means that the first row is zeros. So as you can see, it'll set those as zeros. And I have only put these from 2 to the second last row, second last column. Similarly, the last one is 100, which is this one up here. And you can see how Matlab calls this as 1, this first row, but technically this row represents over here, this side. Similarly, we can define the columns. and now you can see we have our boundary values set there, and we are trying to find these 9 values. So now we're going to go ahead and set up the matrices, find these values, and then plug those back in there. So first of all, I want to show you the block matrix which we have B. This is that is repeated over here, 3 of those, 1, 2, 3, and so we create A1 matrix, which is a block diagonal matrix. So it's BLKDIG command. So I have 3 matrices that form, which is the same block, which forms the 3 diagonal blocks. And then I create a row from my A matrix, which is R, and the 4th entry is 1. Just like this row up here, the 4th entry is 1. And I can use this as in a command called Topless Matrix, where we have these kind of rows, these kind of numbers so it's this row shifted along this direction. This is called a Topless Matrix. So I can tell it that my row and columns are identical, and if I do that, I get this matrix where I have this diagonal and this diagonal showing as 1s. And now I can add A1 and A2 to create my A matrix. So this is just a trick. It doesn't mean that it will work for all the cases, but it will work for the Laplace matrix. Similarly, we create our B matrix, which is defined here, and then using our inverse we find the p-values. So again, this 42.85 is here, and then 33.25 is 2,1, 33.92 is 3,1, and then this 63.16 is over here, 1, 2. So we have to make sure that we assign these values carefully. So here is one way to do it. I am assigning each row separately, and so that puts all of these values here, and I can use the mesh command to see what this function looks like. So this is how the temperature is. So you have 100 degrees Celsius, 0 degrees Celsius, 50, and 75, and this is how the Laplace equation solves for the middle part of the temperature field. Here's a faster way to do this. You can just reshape the P into a 3x3 matrix, so now P becomes that, and then clearly this is not the correct orientation, but P transpose gives you the correct orientation in a reverse order, and so this will also work in the same way and give you your scalar field. So this concludes the tutorial.